electrical equipment a large energy expenditure, ultimately increasing CO2 emissions, especially in countries lacking renewable energy resources. 39. Currently, there are 5 types of recycling processes: pyrometallurgical recovery, physical materials separation, hydrometallurgical metal reclamation, direct recycling method, and biological metals reclamation. The most widely used processes are the first 3 processes listed, as shown in the examples of current lithium-ion battery recycling facilities. The last 2 methods are still on lab or pilot scale, however, they can potentially avoid the largest amount of emission from mining. The pyrometallurgical process involves burning the battery materials with slag, limestone, sand and coke tar produce a metal alloy using a high-temperature furnace. The resulted materials are a metallic alloy, slag and gases. The gases comprise molecules that are evaporated from the electrolyte and binder components. The metal alloy can be separated through hydrometallurgical processes into constituent materials. The slag, which is a mixture of metals aluminum, manganese and lithium, can either be reclaimed by hydrometallurgical processes or used in the cement industry. This process is very versatile and relatively safe. Because there is no pre-sorting needed, it can work with a wide variety of batteries. In addition, because the whole cell is burnt, the metal from the current collectors could help the smelting process, and because of the exothermic reaction of burning electrolytes and plastics, the energy consumption can also be reduced. However, this process still requires relatively higher energy consumption and only a limited number of materials can be reclaimed. Physical materials separation: recovered materials by mechanical crushing and exploiting physical properties of different components such as particle size, density, ferromagnetism and hydrophobicity. Copper, aluminum and steel casing can be recovered by sorting. The remaining materials, called black mass, which is composed of nickel, cobalt, lithium and manganese, need a secondary treatment to recover. For the hydrometallurgical process, the cathode materials need to be crushed to remove the current collector. Then, the cathode materials are leached by aqueous solutions to extract the desired metals from cathode materials. Direct cathode recycling, as the name suggested, extracts materials directly, yielding a cathode power that is ready to be used as new cathode pristine material. This process involves extracting the electrolyte using liquid or supercritical CO2. After the size of their covered components is reduced, the cathode materials can be separated out. For the biological metals reclamation or bioleaching, the process uses microorganisms to digest metal oxides selectively. Then recyclers can reduce these oxides to produce metal nanoparticles. Although bioleaching has been used successfully in the mining industry, this process is still nascent to the recycling industry and plenty of opportunities exists for further investigation. 33, 35, 37. There have been many efforts around the world to promote recycling technologies development and deployment. In the US, the Department of Energy Vehicle Technologies offices, VTO, set up 2 efforts targeting at innovation and practicability of recycling processes. ReCell Lithium Recycling Road Center brings in 3 universities and 3 national labs together to develop innovative, efficient recycling technologies. Most notably, the direct cathode recycling method was developed by the ReCell Center. On the other hand, VTO also set up the Battery Recycling Prize to incentivize American entrepreneurs to find innovative solutions to solve current challenges. 40. Environmental impact. Transition to electric vehicles is estimated to require an 87,000% increase in supply of specific metals by 2060 that need to be mined initially. With recycling, see above, covering part of the demand in future. 41. In the UK alone, it is estimated that switching 31.5 million petrol vehicles to electric would require 207,900 tons of cobalt, 264,600 tons of lithium carbonate, 7,200 tons of neodymium and dysprosium, and 2,362,500 tons of copper, and a worldwide switch would require 40 times these amounts. 42. In 2022, the U.S. government planned to give U.S. states $5 billion over 5 years for electric vehicle chargers. 43. According to IEA 2021 study, mineral supplies need to increase from 400 kilotons in 2020 to 11,800 kilotons in 2040 in order to cover the demand by EV. This increase creates a number of key challenges from supply chain, as 60% of production is concentrated in China, to significant impact on climate and environment as a result of such a large increase in mining operations. 44. Battery cost. In 2010, scientists at the Technical University of Denmark paid $10,000 for a certified EV battery with 25 kWh capacity, i.e. $400/kWh, with no rebates or surcharges. 47. 2 out of 15 battery producers could supply the necessary technical documents about quality and fire safety. 48. In 2010 it was estimated that at most 10 years would pass before the battery price would come down to 1/3. 47. According to a 2010 study by the United States National Research Council, the cost of a lithium-ion battery pack was about $1,700/kWh of usable energy, and considering that a PHEV 10 requires about 2.0 kWh and a PHEV 40 about 8 kWh, the manufacturer cost of the battery pack for a PHEV 10 is around $3,000 and it goes up to $14,000 for a PHEV 40. 49. 50. The MIT Technology Review estimated the cost of automotive battery packs to be between $225 to $500 per kilowatt-hour by 2020. 51. A learning curve of lithium-ion batteries. The price of battery has declined by 97% in 3 decades. 45. 46. Prototypes of 50 Wh/kg lithium-ion polymer battery. New Li-ion cells can provide up to 265 Wh/kg and last through thousands of charging cycles. 2013 study by the American Council for an Energy Efficient Economy reported that battery costs came down from $1,300 kWh in 2007 to $500 kWh in 2012. The U.S. Department of Energy has set cost targets for its sponsored battery research of $300 kWh in 2015 and $125 kWh by 2022. Cost reductions through advances in battery technology and higher production volumes will allow plug-in electric vehicles to be more competitive with conventional internal combustion engine vehicles. 52. In 2016, the world had a Li-ion production capacity of 41.57 GWh. 53. The actual costs for cells are subject to much debate and speculation as most EV manufacturers refuse to discuss this topic in detail. However, in October 2015, car maker GM revealed at their annual Global Business Conference that they expected a price of $145/kWh for Li-ion cells entering 2016. Substantially lower than other analysts' cost estimates. GM also expects a cost of $100 kilowatt-hour by the end of 2021.54, according to a study published in February 2016 by Bloomberg New Energy Finance, NEF. Battery prices fell 65% since 2010 and 35% just in 2015, reaching $350 kilowatt-hour. The study concludes that battery costs are on a trajectory to make electric vehicles without government subsidies as affordable as internal combustion engine cars in most countries by 2022. NEF projects that by 2040, long-range electric cars will cost less than $22,000 expressed in 2016 dollars. NEF expects electric car battery costs to be well below $120 kilowatt-hour by 2030, and to fall further thereafter as new chemistries become available. 56. Battery cost estimate comparison. Battery type A cost, $/kilowatt-hour, Li-ion 202132, 57, Li-ion 20161330, 58, 145, 54, Li-ion 2014200300, 59, Li-ion 2012500600, 60, Li-ion 20124000, 61, Li-ion 2012520650, 62, Li-ion 20127552, 62, Li-ion 20126889, 62, Li-ion 20138001,000, 63, Li-ion 20107550, 64, nickel metal hydride 20044750, 65, nickel metal hydride 20135000550, 63, nickel metal hydride 350, 66, lead acid 256.68. EV parity. Battery prices fell, given economies of scale and new cell chemistries improving energy density. 67, however, general inflationary pressures and rising costs of raw materials and components inhibited price declines in the early 2020s. 67, in 2010, battery professor Paul Norby stated that he believed that lithium batteries will need to double their specific energy and bring down the price from $500, 2010, to $100 per kilowatt-hour capacity in order to make an impact on petrol cars. 68, Citigroup indicates $230 kilowatt-hour. Toyota Prius 2012 plug-ins official page declare 21 kilometers, 13 mi, of range and a battery capacity of 5.2 kilowatt-hour with a ratio of 4 kilometers, 2.5 mi. Kilowatt-hour, while the ADAX 2015 model utility vehicle already reaches 110 kilometers, 68.5 mi, or a ratio of 7.5 kilometers, 4.6 mi, kilowatt-hour. 69. Battery electric cars have an energy consumption between 2.5 miles, 4.0 kilometers, kilowatt-hour, 85 mpge, and 5.0 miles, 8.0 kilometers, kilowatt-hour, 135 mpge. United States Secretary of Energy Stephen Chu predicted costs for a 40-mile range battery will drop from a price in 2008 of $12,000 to $3,600 in 2015 and further to $1,500 by 2020. 70, 71, lithium-ion, Li-poly, aluminum-air batteries and zinc-air batteries have demonstrated specific energies high enough to deliver range and recharge times comparable to conventional fossil-fueled vehicles. Cost parity. Different costs are important. One issue is purchase price, the other issue is total cost of ownership. As of 2015, electric cars are more expensive to initially purchase, but cheaper to run, and in at least some cases total cost of ownership may be lower. According to Caminit al. 2008, new PEVs would become cost-efficient to consumers if battery prices would decrease from $1,300/kWh to about $500/kWh, so that the